All right, let's get right into it. Today, we're looking at what might be one of the biggest showdowns in modern physics. In one corner, you've got the reigning, undefeated champion of gravity for over a century, Albert Einstein. And in the other, a brand new contender stepping up from the strange world of quantum mechanics. And the prize? Well, just our entire understanding of black holes. So here's the big question, the one that's got everybody talking. Do the first ever images we have of black holes actually disprove Einstein's theory of gravity? I know it sounds a little nuts, but it's at the very heart of this story. We finally have actual pictures of black holes, and those pictures, they're telling us something we really didn't expect. So did the very first direct evidence we've ever seen actually break our best theory for describing them? Let's find out.
Okay, so to really get what's happening, we first have to understand the champion in this fight, Einstein's theory of general relativity. For ages, this has been the bedrock of how we see the cosmos.
Think of general relativity, or GR for short, as the official rulebook for gravity. It tells us that massive things like black holes literally warp the fabric of space-time. And everything else, including light, has to follow those curves. This theory has passed every single test we've ever thrown at it, from predicting gravitational waves to making your phone's GPS work. So when it comes to black holes, you'd think GR would be the final word. Now, according to GR, a black hole is supposed to create what we call a shadow, but it's not a shadow in the normal sense. It's this region of darkness, a bit bigger than the black hole's actual event horizon, where gravity gets so intense that it actually bends light away from us, creating this dark silhouette against all the glowing gas behind it. And here's where the power of GR really shows. It doesn't just give us a vague idea, it gives us a super precise number. For Sagittarius A star, that's the supermassive black hole at the center of our own galaxy, GR predicts its shadow should be almost exactly 52 microarcseconds wide. To give you a sense of how tiny that is, it's like trying to see a tennis ball on the surface of the moon from here on Earth. That's the incredibly precise target we were aiming for. So, with that very specific prediction in hand, scientists aimed a telescope the size of a planet at the heart of the Milky Way to check Einstein's math. But the picture that came back was, well, it was a bit of a puzzle. The whole thing was made possible by the Event Horizon Telescope, or EHT. I mean, what an incredible achievement. It's a whole network of telescopes all across the globe, all linked up to create one virtual telescope the size of Earth itself. And in 2022, it delivered the goods, the first ever direct image of Sagittarius A star. We could finally stop theorizing and start measuring. And this is where the story takes a turn. This is where our reigning champion, general relativity, seems to stumble. Because when scientists actually measured the dark region in the middle of that image, it was way smaller than the shadow GR had predicted, like a lot smaller. Just look at the scale of this mismatch. It's wild. GR predicted a dark area of around 52 microarcseconds. The EHT actually observed a dark spot of only about 26 microarcseconds, literally half the expected size. But here's the strangest part. GR's number did match something, but it was the bright glowing ring of gas around the darkness, not the dark area itself. A completely bizarre and unexpected result. You know, in physics, a 5 sigma result is the gold standard for a discovery. It means there's only a 1 in 3.5 million chance it's a fluke. This discrepancy, it's nearly 13 sigma. That's not just an error. It's a result so far off the charts that it basically forces you to question your fundamental assumptions. It's a huge signal that maybe, just maybe, the rulebook is wrong. And that huge opening created an opportunity for a new challenger to step into the ring. This one comes from the long-standing quest for a theory of quantum gravity, a theory that can finally unite Einstein's world of the very big with the quantum world of the very small. And it's called the nexus paradigm. So what is this nexus paradigm? Well, if general relativity sees space-time as the smooth, bendy rubber sheet, the nexus paradigm sees it more like a digital screen made of these incredibly tiny, indivisible pixels. And that one fundamental difference leads to wildly different predictions, especially when you get to an extreme place like the edge of a black hole. So how does this challenger stack up against the real-world data? I mean, just take a look at this table. The numbers are frankly astonishing. The nexus paradigm predicted the dark central region would be about 26 microarcseconds. The EHT measured 26. The theory predicted the bright ring would be about 52 microarcseconds.
The EHT measured 51.8. It's not just close, it's a near-perfect bullseye. And this holds up for both SGR-A star and the other black hole we've imaged, M87 star.
So, okay, we've got one theory that looks like a huge miss and another that looks like a direct hit. But in science, you can't just eyeball it. You need an impartial referee to call the match. And for that, we turn to Bayesian statistical analysis. Our first tool is called chi-squared. Don't worry about the name, just think of it as a mismatch score. A really high score means your theory is a terrible fit for the evidence. A very low score means it's a great fit. Simple as that.
So let's look at the scores. General relativity's prediction for that dark region gets a mismatch score of about 168. That is a terrible fit. The nexus paradigm, on the other hand, combining all the data, gets a score of just 0.006. In our boxing match, this isn't just a win, it's a first-round knockout.
The researchers who ran the numbers put it plainly. This isn't a fluke. They said the new theory shows profound statistical consistency with what the telescope actually saw. We're talking about a confidence level of over 99.99% here. But there's one more test, the ultimate tiebreaker, the Bayes factor. This calculation directly compares the two competing models and spits out a single number that tells you how many times more likely one theory is to be correct than the other, given the exact same evidence. The result? The Bayes factor overwhelmingly favors the nexus paradigm by a factor of 10 to the power of 36. That's a 1 with 36 zeros after it. The odds are so long that there isn't really a word to describe how decisively the data favors the challenger in this specific contest. So, what in the world does this all mean? We have an absolutely astronomical statistical victory for a new theory of quantum gravity. Is it time to just tear up the textbooks? The reason the nexus paradigm seems to fit so well comes right from its core ideas. It predicts that a black hole's critical gravitational radius, that point of no return, is effectively half the size that GR predicts. This one simple change naturally shrinks the dark region and pushes the bright ring of gas right out to where we actually see it. Plus, NP gives you exact formulas for these features, while GR needs incredibly complex supercomputer simulations to even get close. Now, let's be super clear. This doesn't mean we just throw out a century of Einstein's incredible work. General relativity works perfectly almost everywhere else in the universe. But in this one extreme environment, right at the edge of a supermassive black hole, the data we currently have points to the nexus paradigm as a dramatically better explanation for what we're seeing. And that leaves us with a truly fascinating question. Are we looking at the first real observational proof of a theory of quantum gravity? The holy grail that could finally unite all of physics? Or is this an extraordinary claim that still needs far more extraordinary evidence? The battle is far from over, but for the first time, Einstein's theory has a serious challenger, and the ringside seat is right at the very edge of a black hole.